In this video, I want to start discussing the performance of get input. Now, get input is going to be a little bit interesting because we're not going to be able to use, we're not going to be able to use our standard techniques. We're going to have to care actually more somehow about the structure of our tree. So what do I mean? Let's take a look at this trace up on the screen. This trace on the screen basically is just a ton of operations. It's me constantly doing, puts, right? Adding in elements, right? Adding in S, adding in E, adding in A, adding in R. I'm just doing punch and puts, right? You can even imagine, right, in a full example, right, I could have some removals, some updates, I could have all sorts of things. At the end of the day, though, right, I have this, right, I have kind of the resultant tree subject to a bunch of puts and gets. And there's a problem here, because what happens is, well, I could have different things. So what I am looking at here is basically what we call like an average tree, right, or I call it an average case tree, right? So it's like, well, I just have a bunch of stuff, and it's not, too bad. But I could actually have other cases as well, right? Okay, so then I guess then the question is somehow, right, is why does this matter? Why does this matter? Well, the performance of something like get is basically dependent on the length of the path. So let's say I want to search for an element, right? I'm going to always have to start here, right, at the root, right, and then I'll take some, set of twists and turns, right, to get to the node that I want to visit. The performance of get, right, is basically, how many nodes is based on how many nodes I have to traverse to get to that place I'm looking for. And so ideally, right, I would want to have trees where it's like, well, all the paths are relatively short. If all the paths are relatively short, then put and get don't have to do that much work to get to the nodes that they are working with. And the problem is, though, right, is it basically that idea of, that length of that path is dependent on how the tree looks, right? So I have right now, right, this average tree, right? The paths aren't that bad, right? I mean, so this is, that one's a little short, that one's, good. It's a little bit longer, right? That one's pretty good, that one's pretty good, right? These are a little bit longer, right? So some of these, right, these are going to take more time to get to, right? These over here are going to be really easy to get to, right? Some of them take a little bit longer. Ideally, right, what I want is kind of a compact tree, right? I want that tree to have a bunch of short paths. If I have a bunch of short paths, then it's easy for me to get from the root to any particular node. So yeah. Our issue, though, right, is basically that the order in which I add things or remove things may actually have a kind of an impact on how this tree looks. When I say looks, I mean in terms of like the structural shape. They're still going to be BSTs, but how they looked or how they laid out could be a little bit different. So I have kind of these three different cases, right? So I have kind of the average case or typical case, right? That was what we had on the previous slide, which is a tree like this. So my tree here in the middle, basically, right, it's not bad, right? It's not exactly a balanced or complete tree, but it's not bad. What is bad, right, is the case on the left. The case on the left is a stilted tree. So this is, right, another BST, right? This is definitely a valid BST, right, in alphabetical order. But the problem is they're all just going off to the right each time. They're going off to the right, going off to the right, going off to the right. It's going to take me a long time to get to X, right, or S, right? It's going to take me a long time to get there. Versus C or E are pretty easy. This is going to be bad, right? This is going to be bad. This is also what we call somehow the degenerate case. This is the worst case for finding elements in a tree. Okay. The best case, right, is over here, which is when we have a balanced tree, right? A balanced tree basically means everything's really close up to the root, right? We don't have any longer paths. Everything is as close to the root as we can possibly get it. So let's see. So what we care about, right? What we hope to care about, right, is basically that typical case, right? So in general, right, for average use of this data structure, right, how will the performance be, right? That's what we're going to look at a little bit. Now we're not going to do the full algorithm analysis, and I'll tell you guys why in the next slide. But we're going to talk about the result. We won't do the proof for it, but we'll talk about the result. All right. So let's see. Well, so you can look at this, right, in terms of successful search, unsuccessful search. Well, we'll talk about in terms of an unsuccessful search, right? That's kind of like, the worst thing that could happen to us. So here's a question. Let's say I do a get on a node that doesn't exist. How many comparisons will be needed for the worst case tree over here, right? And we'll say that each of these, right, everything has n elements. So how many comparisons will be needed for an unsuccessful search in the worst case? Unsuccessful search in worst case is going to be n, right? So I actually have to worry about n different nodes. What about for the best case, right? A balanced tree, right? How many comparisons would I need there for if I had an unsuccessful search? Well, that'll end up being log n. Okay, much better. For what's in between, there'll actually be kind of there'll be a little bit of a magic number that we'll talk about. Okay. Point is, right, is that basically based on how my trees look, I may end up, right, with this different, structural, different structural features, right, which kind of impact on how long my algorithms take to run, right? Because I have to go and compare more nodes, right? The more nodes you have to compare, the more work you have to do, the longer they take. So I want to avoid this left-hand side whenever I can. For inserts basically, well, we'll probably pay the kind of the same cost, right? It's like, well, if I want to insert z into this worst case, I'm going to have to go all the way to the right, put it on the right hand side of x, right? Versus for best case, right? If I want to put z in, right? Z goes, right over here, right? So they'll both end up basically be paying this cost here, right? So the worst case is basically associated with the linear cost. The best case is associated with the logarithmic cost. All right, and these, right? Well, these are actually both type bounds. So these are both tilde. So it's even better than big O or omega, right? It's basically saying this is the exact result, right? It'll never be better, right? So we can also say that these are both, omega of n as well as tilde, as well as big O of n, right? And the other one's, big O of log n as well as omega of log n. All right. So yeah, that's how it looks for us right now. So yeah, what can we do about that average case? Because we really would like to know the performance for that. So the average case, or the typical case, is the following case. It's basically where we say that we have, so let's say we have a data structure, right, that's this tree. Do a bunch of gets, do a bunch of puts, right, maybe some deletes. If I just do that kind of randomly, right, if I say, hey, there's this pool of elements, right, I'm just going to randomly put them into the tree, what will it look like, right? That's basically what we call the typical case, right, the average case, right? If I just have a pool of things, I know they're going to be put into the tree, let's say I just put them in a random order, what will things look like, right? That's kind of what we're analyzing there. This is in contrast to, for example, the worst case. The worst case is basically saying, oh, what happens if every time I add an element, I'm going to add a large element, right? If I keep adding large elements, I get this splayed thing, right, a stilted thing where it goes all off to the right. Versus that typical case, right, it's like, oh, what if I just add things, what if I just add things in a random order, right? That's what that's what we would look at analyzing. Now for us, we're not actually going to do the full proof for this because it's hard. It's really hard, actually. So I started to do it, right, and I actually debated when I was going through my materials for this class whether I teach or not, and I decided not to, okay? So we're going to jump down to the final result, and I'll maybe tell us a little bit to talk about here. The final result is actually this, right? So if I were to go look for a tilde, right, a very, very tight bound for how long it takes to add something or look something up, well, let's say it looks something up, right? Do a get or put, right, in an average tree, right, a typical tree. I'll actually get this over here. I get 1.39 log n, right? That would be my tilde for something like a get or a put. Okay, that's how the world looks, right? That's our answer to the question. Right, the question was, how many comparisons are needed, right, in the average case, right, for looking up something in a BSD, right? This is our answer. Now there is on the slide a whole lot of other stuff, right? So there is this chunk of text here. This chunk of text here, though, I did teach this one semester, one time. It's just really, 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 really complicated. Because what happens is that in this proof, right, I would probably need like 10 or 20 slides to teach this proof. Basically what this proof does is it's a way of, is in this proof, you basically construct every single possible tree that could ever be built, right? So it's like, well, I could put it to the left or I could put it to the right. So this proof basically is saying, okay, I'm going to say that I have this tree where it went to the left, this tree that went to the right, right? And it keeps doing that again and again and again until it basically has this kind of sum of all the different trees you could ever construct from adding things from adding nodes to a tree, right? All the different trees you could construct, right? Some of them are stilted, some of them are not stilted, some of them are balanced, right? You have all the different possible trees you could ever build, right, from doing the inserts. And then, right, you average them. You average them and get the average length of the path from their root to each of their internal nodes and their leaf nodes, right, to each of their nodes inside. And that construction as a whole, I mean, you can start to see some of it up here. You can see, average of possible subtrees, right, maybe some keywords here. It's really, really complicated. So don't worry about it, right? Just know, so I guess what you should know, and this is really just for fun, is that if you were to analyze this, right, and you were to do this properly, the process is, right, build out every single possible tree that could ever be built by some sequence of puts, and then average the lengths of all the paths inside of them, okay? That's your summary of this proof, right? That's what needs to happen. Now, for that to happen, it's very complicated, and we won't do it, but just in the back of your head, right, kind of know that's the analysis that it would take place. For now, right, the key for us, right, is this thing at the bottom where we say, okay, what, in the average case, it's going to take this 1.39, log n time, right, to find something, which is good, right? Because in terms of big O, that's just log n, right? So we're logarithmic time. So it seems like things will be pretty fast. All right, so that's it for our little brief intermission here. We're talking about performance analysis. In the following videos, we'll go back to implementing the different methods inside of our BSTs.